July 1st, 2025. NASA's telescopes catch something impossible. A comet tearing into our solar system at over 220,000 kilometers per hour. At first, astronomers rally, but then, total silence. Not because they can't explain it, but because what 3IATLAS might truly be matches their deepest fears. 3 interstellar objects in just 8 years. Statistically unthinkable. This comet is moving too fast, on a path so precise it dodges our best instruments, as if guided. Some quietly suspect it's not just wandering space, but returning on schedule, mapping every planet. Why are top scientists afraid to say what's staring us in the face? What if for 8,000 years, something's been watching us, and its observation is nearly over? At 3:12 a.m. UTC on July 1st, 2025, the night shift team at the ATLAS control room in Chile watched a single alert pop up on their monitoring dashboard. The system flagged a faint, fast-moving speck at 4.5 astronomical units, roughly 670 million kilometers out, crossing the inner solar system at 61 kilometers per second. That's faster than any comet ever cataloged by the survey, and nearly double the upper limit for objects bound to the sun. The automated pipeline, tuned to catch near-Earth threats, hesitated. For a few seconds, the object was listed as a possible impactor. Then the trajectory solver kicked in, showing a hyperbolic path, unbound, inbound, and coming from deep space. Inside the control room, the usual chatter on the team's encrypted Slack channel froze. No one sent a message. The protocol called for immediate cross-checks. Pull up Zwicky Transient Facility pre-discovery images, run orbital fits, and alert the Minor Planet Center. But the numbers didn't add up. Eccentricity above 3, inclination nearly retrograde. The object's path cut almost perfectly along the ecliptic, but in the wrong direction, against the flow of every planet in the solar system. The odds of catching a random interstellar traveler on a trajectory this precise? 1 in 20,000, according to the latest Monte Carlo models. By 3:18, the lead astronomer quietly escalated the alert to NASA headquarters. The internal comms log shows a 6-minute gap. No jokes, no speculation, just a silent screen. Veteran scientists who'd spent decades chasing rare asteroids now stared at a set of orbital elements that made no sense. The official classification would wait. But everyone in that room knew this was no ordinary comet. And whatever it was, it had arrived exactly on schedule. Within hours of the initial detection, the world's largest telescopes were already locked onto the new arrival. Hubble's deep imaging picked up a faint, diffuse coma, stretching outward from a central point, clear evidence of outgassing. The James Webb Space Telescope followed, collecting spectra in the near-infrared. These early datasets settled the most urgent question. 3I/Atlas was not a dead rock or a metallic fragment. It was alive, in the way only a comet can be, venting volatile gases as sunlight struck its surface for the first time in millions, or even billions, of years. The nucleus itself defied early speculation. Photometric modeling, using both Hubble and ground-based data, set the diameter at less than 6 kilometers. That's small by comet standards, but not unprecedented. The coma's shape and brightness matched the familiar physics of sublimating ices, with jets of carbon dioxide and water vapor driving a classic dust tail. No sign of artificial reflectors, No unexplained surges in luminosity, just the slow, steady brightening that comes with inbound motion toward the sun. For the scientific teams, the process was methodical. Every anomaly got a second look. Every fit was cross-checked against the archives of Oumuamua and Borisov. The consensus formed quickly. This was the third confirmed interstellar object ever observed, a true comet by every measure available. The excitement was real, but so was the discipline. Benchmarking against decades of cometary science, researchers built their case on coma morphology and nucleus photometry, not wild speculation. In the end, the evidence pointed to a rare but natural visitor, one that just happened to be passing through at exactly the right moment. Monte Carlo analysts at NASA and JPL spent the days after discovery running millions of simulated arrivals. Each one, a hypothetical interstellar traveler, was assigned a random speed and direction, then flung toward the solar system on a digital coin toss. Most missed the ecliptic by a wide margin, veering off into the void or swinging high above the planetary plane. A handful cut through the solar system, but almost none matched the retrograde, nearly head-on approach of 3IATLAS. Out of 20,000 simulated objects, only one followed a path this tightly aligned, skimming just a few degrees from the ecliptic, but moving against the flow of every planet. Statistically, it's the equivalent of threading a needle from across a football field. The orbit's geometry raised eyebrows even among the most skeptical dynamicists. 3IATLAS wasn't just coming in fast. Its trajectory set up a sequence of planetary flybys that looked almost choreographed. Mars first, then a distant pass by Venus, and a wide swing past Jupiter. Each encounter fell within a narrow window, close enough for gravitational nudges, but never enough to trap or deflect it. The odds of a random interstellar object weaving through this planetary gauntlet on a retrograde track nearly flush with the solar system's main plane are vanishingly small. The covariance matrices from the best-fit orbital solutions left little room for error. Even after correcting for survey bias, factoring in Atlas's ecliptic-focused search pattern and detection thresholds, the numbers refused to budge, 1 in 20,000 or rarer. For the statisticians, the data didn't just challenge intuition, it demanded a new kind of caution. In the world of orbital dynamics, rare events are expected, but this particular combination, hyperbolic escape, retrograde motion, and a planetary grand tour, sat at the farthest edge of the probability curve. The question wasn't just how it got here, but whether chance alone could really account for such a precise arrival. Spectroscopy teams at the Very Large Telescope worked through the night, calibrating every emission line from the incoming comet. The early spectra told a story no one expected. Cyanogen, usually one of the first gases to show up as a comet heats, was missing. Deep integrations at 388 nanometers came up empty, even as carbon dioxide lines blazed at record strength. That's not just odd. In the catalog of solar system comets, it's nearly unheard of. Some argued for a dust crust, thick enough to bury cyanide ices until late activation. Others pointed to thermal models, suggesting the parent star system could have baked out the lightest volatiles billions of years ago. Then came the metals. Nickel lines flashed in the ultraviolet, but iron stayed stubbornly invisible. Lab analogs show nickel and iron usually travel together in cosmic dust. Here, nickel outshone iron by a factor of 50. That ratio doesn't match any known meteorite or comet sample. Mission coordinators flagged the anomaly for urgent follow-up, pushing for more time on the James Webb Space Telescope and ground-based spectrographs. October 2025 became a red-letter window. Mars orbiters would have a shot at the coma as 3I/ATLAS made its closest approach, and the Vera Rubin Observatory was set to sweep the object's outbound path for lingering dust. Every new spectrum forced the chemistry teams to revise their models. The calibration debates spilled into Slack threads and late-night calls, with instrument scientists arguing over background subtraction and line blending. But the consensus held. The object's chemistry didn't fit any natural template. And with the clock ticking toward the next observation window, the pressure to find answers kept growing. Avi Loeb, a Harvard astrophysicist known for courting controversy, didn't wait for consensus. He ran the numbers on 3I/ATLAS's energy budget, comparing its brightness curve to the sunlight it should reflect. The result? If the object were generating its own light, even at a fraction of its observed luminosity, the power required would rival a nuclear reactor, orders of magnitude above any known natural process for a comet this size. Loeb pointed to the trajectory as well. The inbound path, nearly flush with the ecliptic but retrograde, mimicked a flight plan designed to maximize planetary encounters while minimizing detection windows from Earth. He called it a cosmic reconnaissance maneuver, akin to an engineered Oberth slingshot, but in reverse. For Loeb, the odds of such a trajectory occurring by chance, 1 in 20,000, weren't just unlikely. They demanded a closer look at the possibility of intent. For early career researchers, the 3I/ATLAS debate became a minefield. Junior scientists watched as online speculation spiraled and media outlets latched onto every hint of controversy. Editorial boards sent out reminders about responsible communication, warning that careless statements could jeopardize grants or future telescope access. Some postdocs quietly scrubbed their social media, worried that a stray comment might land them on the wrong side of a peer review. In internal Slack channels, the tone turned cautious. Questions about artificial origins brought private support, but public silence. The fear wasn't about aliens. It was about being quoted out of context, or worse, dismissed as reckless by colleagues who controlled the next round of proposals. For every headline chasing the unknown, there was a young scientist calculating the cost of curiosity. On July 1st, 2025, NASA's ATLAS team detected 3I/ATLAS traveling at 61 kilometers per second, faster than any known comet. Detailed analysis revealed a 1 in 20,000 trajectory, missing cyanogen in its spectrum, and an unexplained brightness requiring up to 10 gigawatts of power. Peer-reviewed studies confirm its origin from the ancient galactic thick disk, with pristine water ice older than Earth. While mainstream scientists emphasize natural models, a vocal minority highlight evidence for artificial propulsion and surveillance patterns spanning 8,000 years. To date, no official document explains the absence of key molecules or the object's repeated solar system visits. The upcoming James Webb and Mars Reconnaissance Orbiter observations are scheduled to provide new data in October 2025. Until then, 3I/ATLAS remains the most statistically improbable and chemically puzzling visitor ever recorded, forcing the scientific community to confront questions that remain unresolved.